Um, so, let's see. I always make notes. My wife encourages me to make notes up here, but then I forget it and I have to read it. So it's better just to stumble through. So the offices from last meeting in December, the resident officers, the incumbents, were largely re-elected. So thank you all again, I think. We have, also we have one change. Andy Allen, is he here?
Hey.
Come on up here. And he's our secretary for 2024. He's changing that position. We're going to have Tessa Flanagan. She's here somewhere.
Tessa?
Oh, she's.
Oh.
Do we have a swearing-in ceremony?
No, we're just going to give him an award for our appreciation of his excellent work. Oh, so, secretary for 2024. Appreciate your work.
Thanks.
Let's see. The Telescope Tuesday. Telescope Wednesday, not Telescope Tuesday, that's the competitor. The Telescope Workshop on every Tuesday night will start back up next Tuesday. We were off for the holidays. I was out of town and otherwise decaned.
Yeah, is that Zoom only? Sure.
Yeah, we covered that. We gave an award to Andy for his past work.
Jerry, telescope, is that Zoom only?
What's that?
Is the telescope maker Zoom only?
The Telescope Tuesday, the Telescope Workshop.
Right.
They're starting up again every Tuesday from 7:30 to 9.
Is it Zoom only or are you in person?
It's Zoom only. We have so many people that we have about 6 to 8 regulars, and about half of them are out of town. Tascadero and San Francisco, and Phoenix, Arizona, Tucson, Arizona. And so they couldn't make it to an on-site website. So that pretty well precludes our previous major activity of mirror making. So we can still guide you through mirror making. Chuck?
Just a question, is Bob Richard still attending?
He is not attending regularly, but every now and then we hear from him. He has something he wants to show us, and so he reserves,
Okay.
a Tuesday.
Because I noticed his webpage went out of commission.
Yeah,
Had me a little worried.
yeah. Well, I share your worry. He's not as regular as he used to be. We also have Telescope Tuesday, which is the third Tuesday of each. First Tuesday of each one. So that it's going to conflict with the workshop this coming Tuesday. But oh, okay. Tom, did you hear that?
No, I didn't hear it.
Someone said that it looks like I'm talking, but they can't hear me, so they think I'm muted here.
So,
Yeah, and someone else is chiming in. They don't hear me
Damian, you
either.
think there's a...
Can you hear me now? Hello? Did we cut you off completely, or can you hear us? They're not responding. I can't hear them.
Let's see, maybe audio is good.
So, okay, good. Thank you. That's all I needed. Okay, good. Okay. So our holiday dinner at the Timbers was very successful, very enjoyable. There was a little bit of miscommunication about the time to start. I showed up a half hour late because I came on time for the advertised time. So that is, Chuck has agreed to take over editing everything that we're doing so it's all consistent and shows the right type of, the right dates. So, but for the Christmas holiday dinner, thank you, Diane Wilkenbach. We look forward to future events. So we're now going to go through some formalities here, business stuff, before our vice president gets up and introduces our speaker.
Well, you got 2 other people coming up too, right?
Yeah. Yes, you're the third. Don't look on him as last. We have As you see, we have merchandise up here, which our merch manager will go over for you.
Yay, back.
My name is Pat McPartland, and I'm the merch manager for the club. And one of the things that we sell is a tote bag, which is really cool. It has all sorts of pockets, and you would find all sorts of uses for it. We also have mugs tonight and some caps up there too. So if you are interested in buying anything, let me know. And I've got all sorts of clothing that I couldn't fit into poor Farron. But if we're back into Fleischmann, I'll have it fit, it'll fit in there. So merch manager, and my email is merch, MERCH, MGR @SBAU.org. Thank you.
And now Chuck will do our outreach for the coming month.
Chuck, I gave you a special slide coming up here.
Uh-oh.
And here it is. You can explain this to us.
Oh, yeah. Thank you, Jerry. One of the things I do for fun for citizen science is asteroid occultations. And so there's a group called IOTA, International Occultation Timing Association, that handles the data and comes up with good astrometry and stuff like that. And one of the things that happened was there was a new asteroidal type object that was detected, and they gave it the usual designation 2018 CN41. So that means they found it in 2018, and the first letter is the week of the year in 2-week chunks, and then they go through the alphabet after that, and then this was 41. So you can see they're finding a lot of stuff. But they announced it in 2025 once they got an orbit on it. And sure enough, when they looked more closely at the orbit, they found out it's the Tesla Roadster in its orbit out there, coming from Mars with the Starman, the little dummy sitting in it. So I sent that out to some of the people that are interested in that kind of stuff. Okay, so outreach-wise, I do have final statistics for 2024. We had 29 volunteers who had 6 or more events in 2024, so they get their membership extended for a year. And we had about 42 people overall that came out and helped out. That's not all of them, because we have spouses and significant others and stuff, some people who may have showed up and I didn't see them. We had 147 events, which is way down from normal. We used to do 210. But that's because we lost Bacara, and a lot of the schools up in San Ynez aren't calling us anymore. But we had attendance of 12,245, so that brings us up over 270,000, so we've gone past the moon. And we had about 2,121 volunteer hours, so that was our outreach for last year. And for this month, what do we have? We have tonight's meeting. We have on the 7th, Tuesday, coming up is the Telescope Tuesday at Commuter Rail Marketplace. We move the Tuesdays around to try to make sure we have a lot of first quarter moons to look at, because there's so much light there. So that's why we switch around, but now it's first Tuesday of the month. And then that always starts at 7, goes till 10, because we'll have a moon to look at most of the time. Then coming up on the 10th, on Friday the 10th, we have telescopes for Fusion Academy. They don't really have a campus that's amenable to setting up telescopes. It's right downtown, and they just have a parking lot, and it's covered with lights. So we're going to set up on the east end of Shoreline Park. Setup will be at 5 p.m., and they're going to show up at 6, and we'll show them the sky. Hopefully we'll have good weather. And then second Saturday, the 11th, is the Santa Barbara Museum Natural History Store Party right here. And so we'll be starting at 7, so set up at 6. And before that, we'll have our planning meeting. That's at 4. That's on Zoom.
Wait, so you're not doing anything for the Moon and Mars thing?
No, we're not doing any special outreach thing for that, just because it's hard to find a venue that a lot of the public could come to where they could see that. Although Shoreline Park probably would work okay. But it's really low, and anyway. Okay, and then on the 15th, Wednesday the 15th, Mountain View School Science Night. set up at 4 p.m. and they go from 5:30 to 7, and they usually have pizza and other goodies for volunteers. And then on the 17th, third Friday of every month, is our regular Westmont Public Telescope Night. And there's actually, assuming the weather's good, there's a 100% rated asteroid occultation that night of an asteroid called Callisto, which has a weird shape. So I'll try to do that, and if anybody wants to, they can come and watch. And then on the 23rd, Thursday, is Brandon School, their science night. And we set up kind of in the middle of their campus quadrangle. There's a little elevated concrete pad that we set up on. And they usually have goodies for volunteers. And then on the 29th is Santa Barbara Junior High School. So we'll be set up behind the Marjorie Loop Theater. So you have to enter, well, traditionally we've entered coming from kind of the north side of Ortega Park. And there are two streets that intersect there, but they dead end in the park and the school. And we come in through a gate there and come around to behind the Marjorie Loop Theater through an open gate. Last year we showed up and the gate wasn't open, and they had opened a gate on the other side of the campus. So if you come and you see that that gate's closed, try going around to the main parking lot and going as far back as you can, and there may be a way through there. I don't know which one they're going to open this year.
Chuck, are you doing a talk there?
I'll do a talk in the Marjorie Loop Theater for the students, and then we'll have telescopes set out at back afterwards. And then coming up on the 31st, it's not really a public event, but for AU people who are validated volunteers, the folks out of Hollister Ranch asked us to come out and do an event at their Bolito Beach site. And I'll be sending out coordinates for that because it's kind of obscure to get to out there at Hollister Ranch. But I need people to notify me if they're going to come, because we need to give them a list of names. And this year they've added another wrinkle. They're going to send me a release of liability form that everybody will have to sign. And I don't know whether they're going to send that to me and expect other people to email it in, or they're going to expect people to print it out and bring it with them, or if they're going to just have printed copies at the gate that you sign. One year they had them at the gate and you just signed them as you came in. So
That should be pretty dark out there.
it's nice and dark out there, yes. It's a beautiful sight. And they're going to have a potluck, so I don't think they expect us to bring anything, but we usually bring some desserts or something like that. Observing aids. So that's it for January. Thank you.
Thank you, Chuck. And now to our main feature, the speaker for this evening. Well, all right. And our Vice President, Ronnie Heron, will introduce him.
Happy New Year, Mr. President.
Jerry?
What? Oh, Tessa.
You're in the shadow, but I
Oh,
think it's...
a quick secretary's report to folks. A whole lot of us joined the SBAU in March, so you'll be getting a reminder notice by email in like a week and a half. And if you don't want to be bothered with that, just make sure you hand a $20 bill to Pat or me. Make sure we have your name, so we have that recorded, and then I'll send you a receipt of that. And if you've had any change in contact information, if you've moved, if you've changed your email, please let us know about that as well. Thank you.
Thank you. Sorry I skipped you.
Our new secretary, yes. She's good. Got a wave at us so we know who she is. You already sent out the connection to what? This tonight, right? The Zoom.
Correct.
That was you, not Andy. But I'm glad
That
Andy
was me. That was Andy to the newsletter. Thank you.
Okay. Well, Mr. President, thank you very much.
And I got lots of notes, but I'm going to skip right through them because tonight's a good one. The search for planets orbiting nearby stars, with our special guest from CSUN in a moment. Let me get a couple things done. I always try to find out who's here. We want to know among the crowd. Raise your hand if this is your first visit, first time ever.
Yay.
Oh,
Nice.
okay, that sounds good. Oh, you don't want to see my face. Why am I not seeing my face?
Push it back.
Oh, not really, but that's okay. Who is that? Joe, the guy that was on the screen a second ago? Was that him talking? We have lots of members here, so the rest of you, raise your hand if you're a member.
Yay.
About the cost of a meal with a drink at Harry's for a year with us, $20. And I believe you can get it free if you go to a lot of church outreaches. I want to welcome you aboard. I want to say thank you on behalf of the four of us, the slate from a month ago. It was a hard-fought, close race, as you well know. I was ready to protest if I didn't make it. I would say I did anyway. That seems to work in politics these days. So we did our show of hands. I wanted to thank the speakers from last month, but I don't think they're here. Dr. Sean Kelly, are you here? From City College. And Farshad Barman, did you make it back?
Nope.
Okay, they're still recovering from doing their speeches. And we got lots to talk about. Tessa is on board, and Andy's still with us. I wanted to introduce you to a friend of mine who may be doing a speech, because I'm going to give our monthly speakers for the next 4 months in a second here before I introduce our esteemed guest. But a dear friend of mine came out of the woodwork from years ago. I used to interview him when he was in town pushing the symphony. He was the PR guy for our Santa Barbara Symphony. And before that, I believe he ran the music department at Paramount Studios in Hollywood. And he wrote an article last spring, I think, or this last year, that was the cover story of Astronomy Magazine called The Sound of the Cosmos. And he gave me a copy, and that was just awesome. Somehow he's introduced sound, and we're not talking about those explosions in Star Wars that you're not supposed to be able to hear. But apparently they turn radio waves or something into the sounds. And he's got a second one coming out, and I want to introduce him. He's a dear friend of mine sitting next to me, David Grossman. Would you stand up and wave at everybody? He's in the club. You don't know when it'll be published again, the second one. It's called The Sound of the Cosmos. We're going to try to get him to speak to us, and he'll be able to add sound effects, I hope, if we get you. But let me tell you before I bring out our guest, who's coming to town. A month from today, or at least the first Friday of February, it's Dr. Shamindu Amara Singh. Young guy just got his postdoc, he got his doctorate, taking us down a mile-deep shaft in the Black Hills of South Dakota looking for dark matter. They got a continuing experiment involving a big machine that's filled with liquid xenon, I think, and it detects WIMPs. That'll be our speech in a month. March 7th, with help from Isla Jade Komasa from the museum, a renowned author and astrophysicist, Dr. Jeff Bennett, will be in town anyway. He's written books, and he covers everything from children's stuff to, this speech will be beyond UFOs, perhaps, let's see, extraterrestrials, covering extraterrestrials. So he's going to continue on from what Dr. Christian's going to be talking on, bringing in the life. You're going to take us out and find the planets, and this guy in March, 2 months from now, will find out if they're detecting any life on those planets. May 2nd, let's see, we're working on getting our speaker, a NASA guy who actually piloted the little helicopter on Mars called Ingenuity. And his name is Martin Kakin. And he happens to be our president's godson. First time I tried, he was still involved with NASA and JPL and couldn't get back to me, but he said he's now they grounded the helicopter on Mars. He's done.
It's now a weather station.
It's now a weather station. And I guess he sat with a joystick. So I'm working on him. Unfortunately, he said he can't come in May, but he'd come in June. And in June is when we do our potluck. Except last summer, we moved it to July. Diane, are you here?
It's not.
Diane's not here. Our events lady. Well, we're going to have a big meeting next Saturday afternoon before the night show. Yeah. And something that appeared on the screen you didn't mention. You mentioned the Telescope Tuesdays. We do a podcast that's awesome as all get out. I happen to be privileged to be the manager of it, or the host. The president is responsible, and we're about to start our 4th year in March. We just passed the 200 mark every Monday morning. Is it up there? Yep. It's called the Astro Hour, SBAU Astro Hour. Go to YouTube and SBAU Astro Hour. We'll get it. We're live most of the time. We have as many problems getting online for that as we do here at night. So without further ado, let's meet the man from Cal State Northridge, the search for planets orbiting nearby stars. The man received his PhD from the University of Maryland back in '93 in astronomy. Dr. Gene Swank of NASA's Goddard Space Flight Center and the late Andrew Wilson of UMD were his thesis advisors. The man studied X-rays, a collection of X-rays at binary stars, accreting neutron stars, observed with NASA's HEAU-2, the Einstein X-ray Observatory. He'll tell you about that proudly. The man's an undergrad in astronomy, got it from Penn State in 1985, worked several NASA missions, the EUVE, I assume they pronounce that UVA perhaps, FUSE, F-U-S-E, and the Hubble scope, before being a postdoctoral resident fellow at Queen's University, Belfast, Northern Ireland. That was between 2003 and 2008. And he searched for exoplanets. He did that with the Super WASP project. Became professor of astronomy at Cal State Northridge back in 2008. He and his wife, Carolyn, have driven up here tonight. I'd like to introduce him right now, Dr. Damian Christian. Damian J. Thank you, sir.
Thanks very much. Can you hear me okay?
Yeah.
So Tom, should I share my screen now?
Yes, please.
Can you see that okay? Yes. Yeah, well, thank you for the great planetarium show and the nice introduction.
What's that? I hope so. I don't see anything about it being muted.
So yeah, I was working at Space Telescope in the early 2000s, and it was a great job, but it was a job, so I wanted to get to go to the telescope. So there was a position over at Queen's University in Northern Ireland in Belfast, and so I took it to go there to do stellar spectroscopy, but I was lucky that they were building Super WASP, the wide-angle search for planets, and you know, in the early 2000s, there were only a handful of transiting exoplanets known. We had just discovered the first sort of confirmed exoplanet in the modern era called 51 Peg that Didier Queloz and Michel Mayor discovered, and of course they get the Nobel Prize for that about 8 years ago now. So we had this idea to sort of look for transiting exoplanets, and so Super WASP was a collaboration of about 7 universities, and of course ING and La Palma, in the Canary Islands west of Spain. You have they copied one of the Kecks and they put it there as a 10 meter, 0.2 meters bigger than Keck. They always tell you that when you go there. And so then on La Palma, on that observatory run by the Isaac Newton group, who were displaced there from the Royal Greenwich Observatory, there's still astronomers that complain about that, because even though it wasn't the greatest skies, they didn't want to leave RGO. So I was lucky enough to sort of work on this wide-angle search for planets, and so my talk is sort of divided into 3 parts. We'll sort of review some of the methods and the expectations from about 30 years ago, and then I'll talk about sort of the one method that gives us lots of planets and a lot of bang for your buck. You can look at thousands of stars and hopefully detect hundreds of exoplanets. And then we'll talk a little bit about sort of the next big goal is to find an Earth-like planet. And of course, an Earth-like planet that can have a habitable zone and liquid water and intelligent life if we ever find it anywhere. So And then there's really an exciting thing now, especially with James Webb, that you can watch the starlight come through the atmosphere of the exoplanet and possibly look for signatures of life like ozone. And there's a recent press release from James Webb about DMS, dimethyl sulfate or sulfide, which may be signs of life. So there'll probably be a lot of press releases about transmission spectroscopy, measuring the exoplanet atmospheres this year. And feel free to ask any questions. I'm not gonna, go on for more than 3 hours. But, so it turns out that back in the sort of mid-90s, there was sort of this sorry. Maybe I have to hold my. So in the mid-90s, we sort of had this, or in the late 80s, there's been a number of false claims about exoplanets in the modern era, and there was really an expectation that we would sort of find analogs of our solar system, that is the rocky, dense planets on the inside and sort of the gas giants and liquid giants on the outside in 10-year plus orbits. And so this was kind of the expectation in the early 1990s, and of course David Latham had a planet that now is sort of a brown dwarf. It's too massive to be a planet, but it wasn't until 51 Peg was discovered by the Swiss group in 1995 that we had sort of our first exoplanet in the modern era. And just, I don't want to talk too much about this, but if you have more than about 8% the mass of the sun, that is 80 Jupiter masses, an object, a star, can be born to confuse hydrogen into helium. If it's too small, then it's a failed star that we like to call a brown dwarf. If you sort of take an image, you think with the methane and ammonia, it sort of has a muddy appearance, so they nickname them brown dwarfs. But a planet is something that's less than about 13 times the mass of Jupiter. And so there's the Exoplanet Encyclopedia that has tons of planets over 13 Jupiter masses because they want to call everything a planet. But if you go to the IPAC, the Caltech infrared processing facility, they have a sort of the most current website, and things above about 13 Jupiter masses are failed stars, that is, they're brown dwarfs. And so if you look sort of back in the 2000s, and when my friend Paul Butler, who discovered a lot of exoplanets in sort of after 51 Peg in the late 90s, there was sort of a feeling that people would never discover a true exoplanet, that it would always be sort of a failed star or something else. And so you can see back 1995 it's 0, and then there's the pulsar planets, which are small rocky bodies orbiting a dead star called a neutron star. And then of course you go into the 2000s, the sort of green is radial velocities, the Doppler method that was done at Lick Observatory, and then Keck. And so now we've had just bursts with Kepler. You can see the Kepler data coming in, the purple with the transiting planets. And now there's almost 6,000 exoplanets known, over 5,800. And so it's really sort of taken off. And here is sort of it's updated on my screen, but not there. Did it go forward?
Yeah.
There it goes, yeah. So you can see this is sort of the definitive site, and if anybody wants a copy of my slides, I'm happy to, it's 40 megabytes, but I'm happy to share it. And so it turns out there was a real big surprise in the early 90s that a lot of these exoplanets were in really short orbits, which I'll show you in a minute, 3 and 4 day orbits, and a lot of really talented astronomers said these can't be planets, they must be star spots or things like that. But even now, there's still about 1 in 5 are these what we call hot Jupiters. They're zipping around their planet every 4 days. They're 25 times closer to their star than we are to the sun. But this is sort of the definitive resource now, this NextSci website. If you want, it's open to the public. You can, people like Scott Gowdy at Ohio State, they write papers on the different statistics, looking at all the fun parameters of exoplanets, because there's so many of them now. And so now I'd like to move in to talk about some of the methods. And just a quick definition that you probably are familiar with, the fact that if we're sort of lucky enough to be looking face on in the system, you might be able to see the planet through imaging where, you know, the planet is orbiting around the star here in blue, and of course they're orbiting their common center of mass. The more massive the planet, the bigger the wobble is going to be, and we call that face on. But then to sort of do the Doppler or the transit method, you have to be sort of lucky enough to be looking edge on, and then you can see if the Jupiter or smaller planet goes in front of the star, it'll dim the light. And so you have to be a little bit lucky. You're going to be more sensitive to short periods, more massive planets, and, you know, sort of inclinations that are closer to edge on. And so I wasn't going to spend, give it a second, catch up. So it turns out Alex Wolzakan detected some planets back in 1992 using radio, the pulsar timing method, where these pulsars that spin 1,000 times a second, their periods were sort of tweaked a little because they had this planet there, and they've even detected sort of an Earth mass planet going back to 1992, but they're not sort of planets we can go and find life around, so we really don't, just for completeness, I'll put that in there, but the one method is if you're face on, you can sort of detect astrometry. Currently, there are only sort of 3 systems known that have been detected with astrometry, but, and there's a little cartoon of a planet and star going around our common center of mass. But my former student, who's at IPAC now in the Exo-Planet group, he sort of had heard a rumor that Gaia, which is measuring astrometry of hundreds of thousands of stars, it's a European space mission doing really accurate imaging so it can measure the positions of stars to 1,000th of an arc second, a really tiny angle. And so they're supposed to dump 10,000 exoplanet candidates this year. So that'll be interesting when that happens. Job secure. So it turns out that we may be getting a lot of astrometric exoplanets soon. And then gravitational lensing, I was going to sort of, just like we saw in the planetarium with the black hole Sagittarius A star distorting the light behind it, because gravity tells space how to curve, and then space can tell matter and light how to move. If you're lucky enough to have this chance alignment with a foreground star sort of acting as the lens, enhancing the light of a background star, and you add a planet, that planet can act like a defect in the lens and cause an extra magnification, even sort of 2 magnitudes, a factor of 5 to 6. And so there's hundreds of microlensing planets that have been discovered. The downside, even though they can find really low mass planets, most of them are thousands of light years away. So it's not a way to find nearby stars that we can go visit.
And you see them once.
What's that?
And you see them like once.
Yeah, it doesn't happen again. The chance alignment takes probably millions of years, or don't quote me. Oh yeah, so there's a little gravitational lens event where you can see where you get sort of 2 magnitudes increase from the star lining up, and then the planet acts, and then Keith Horn used to call it a defect in the lens. And then as the planet goes through the lens, it magnifies it, and you can actually measure its parameters really accurately and do Earth mass planets. But again, this chance alignment takes sort of the background stars towards the galactic center, so you're talking, thousands of light years. And now direct imaging, you might think that this is the way to go. So this was one of the first planets imaged with this adaptive optics system on the 8-meter down in Chile, the VLT. And so this red thing is a planet, probably a massive planet around 10 times the mass of Jupiter. And this is a low mass star, which would be actually a very red object, but they colored it like that. And it's at 55 Earth-Sun distances, so it's way out there in a Pluto-like orbit. And so they nicknamed this thing the Giant Planetary companion candidate in 2010, I believe. And as you may have guessed, it did not catch on. But the most important point here is that planets are about 1 billion times fainter than their host star. And so here's the sun compared to Jupiter. Here it's sort of, 1 micron. Here's the optical over here. You can see that the sun is about 1 billion times brighter. As you go to longer wavelengths, it gets better. But, we're sort of up against it. If you want to try to image planets, you're going to have to, younger, hotter planets in the infrared are going to be more easily detectable, but you're still talking 100,000 to 1 million times fainter. And I have this little demo. Which may or not work very well in the lights, but let's see here. All right, can you see this little red light in here? You see this little red light? You believe me, there's a little red light in there? It's not a magician. So that's like a 1 watt LED. So now I'm going to turn on the 100 watt star. So now I've turned on a 100 watt LED bulb. So can you still see the planet? The little one? No chance. And that's 1 part in 100. So technician Victor built that for me. So yeah, it's really, there's a planet. The simulated planet available at Kmart. So anyway, so to image planets is actually very difficult. You need a really big telescope. You need to collect a lot of light. You need to know the scattering of your telescope and all that good stuff. And so we were lucky. So this is a Hubble Space Telescope image of a relatively bright star called Fomalhaut, which back 20 years ago, now 21 years ago, it detected these little infrared bumps. And so that was kind of the poster child for, but this is sort of an older disk. These aren't really young planets. But then there was a famous system, an F star called HR 8799, where now you can see over several decades of observing this thing, where there's now 4 planets. There may be a 5th, but they're sort of in really long orbits. So yeah, so it has one that's in a 470-year orbit, and of course, astronomers have really dropped the ball in naming exoplanets. People wanted fancy names like Bellerophon or 51 Peg, but they're B. So the first planet is B, the second planet is C, and D, and E, and so on. And so I think there's an E planet now in HR 8799. We can see HR 8799 is sort of the poster child because it's a young system. These planets are hot, so they're only about 100,000 times fainter than their host star. And of course, you use a special instrument to block out the starlight so that you can see these planets. And so there's about 100 planets that have been imaged now with mostly 8 and 10 meter telescopes like Keck and Gemini and the VLT. But there's an astronomer at IPAC, she insists we haven't imaged any planets because if you're going to be really pedantic, we're seeing their infrared emission. We're not really seeing the reflected light. But that's, well, question, yeah?
What sort of distances are you talking about these stars and solar systems?
It's on the bottom left.
Yeah, this.
For the star itself, how far
yeah,
away?
I think we could do that. I think this is about, I forget exactly, 30, maybe about 100 light years away.
Okay.
I'll look it up. I don't.
I think there's another question down the center here too.
Yeah, yep, go ahead.
I know it's probably really basic, but you're calling the star, but it would be as though it's our sun. And these are orbiting around.
Yeah, so this is a star that's much younger than our sun and slightly hotter and brighter. Yeah. Yeah, so we.
130 light years away.
All right, thank you. Yes, 130 light years away. So it's 100. Yeah, go ahead.
Professor, you mentioned earlier the orbiting
Yeah.
neutron stars.
Yeah.
Can we see those? They're not right.
No, they're not bright. We see them in the radio because they're acting like the lighthouse model, you know, that big magnetic field, so then they give us a pulse of light every time they point towards the Earth.
But that doesn't detect the planet.
Well, but because the timing is delayed, or as the planet goes around it, you know, it's on one side, it speeds it up, it's on the other side, it slows it down, so they were able to see these minute changes that they can model as a planet, yeah.
At one time, those planets orbited a full star and it decided to...
Probably, or they could be debris left over after the supernova, so you can argue about that. Yeah. Oh, good question. So now we come to sort of the two workhorse methods that have really discovered the majority of exoplanets, measuring the Doppler shift. And I won't spend too much time on this, but we're all familiar with the Doppler shift, the fact that as a source moves towards you, the sound wave can get compressed. It goes to shorter wavelength and higher pitch. And as it goes away, right, it gets stretched out. And light behaves the same way as sound, so that when a star is wobbling towards you, those wavelengths are squished to the blue part of the spectrum. They're made shorter. When it wobbles away, then that light is stretched and it's redshifted or spread out. And so this was sort of the technique for finding exoplanets that Butler and Marcy up at UC Berkeley were working on, and Michel Mayor and Didier Cluse were doing it. And so this was the first exoplanet in the modern era. Well, you can't see this little green dot, which is the planet, but as the planet goes away, the star wobbles towards us. It's only about 80 silicon atoms on your detector, but that tiny blue shift in wavelength allows you to sort of measure. And of course, 51 Peg is kind of unique. It's actually a pretty massive planet. Let's see, it's about half the mass of Jupiter. And these are really big amplitudes, 50 meters per second. Most of our exoplanets have, 5 to 10 meters per second. So, and it's sort of ironic, this was kicked out. Butler and Marcy had a list of about 14,000 nearby stars. 51 Peg was excluded because it was it was listed as a giant star in some other list, so they didn't include it. And Michel Mayor and Didier Cluse sort of beat them to it. But this is lick data in 1995, right after they had announced it. They went and confirmed it, in a month worth of data at Lick on the old 3 meter. And so since that time, if you're talking sort of the late 90s, there were sort of maybe a dozen exoplanets known, and then maybe by the turn of the century, 100 from radial velocity surveys. And then one of the interesting things is David Gray is a pretty well-known astronomer. Him and Artie wrote this paper claiming that these are star spots, and it says the planet hypothesis is no longer viable. So this is 1995, I think, 1997. So there were some naysayers because people didn't really believe that you could move a planet into a star and have it in a 4-day orbit without it falling into the star, right? So probably would like to retract this paper. And so then finally, sort of the workhorse method that I've been involved with is photometric transits, where if you're lucky enough to be looking edge on, and the hot Jupiter goes in, it's sort of 10 times smaller, so as the hot Jupiter goes in between us and the star, it's going to dim the light about 1 part in 100 or 1%. And you have to sort of do good photometry, but you can detect this from ground-based, from a relatively small telescope. Later, when we get smaller planets, we'll see that for an Earth-sized planet, you got to do that from space. That's only going to, because it's 100 times smaller now, that only dims light 1 part in 10,000. And that's why Bill Barucki pushed and pushed. It took probably close to 2 decades for him to get Kepler funded and launched, where now from space you can detect Earth-sized planets. And so here's one of the,
How'd that happen? We lost your, reconnecting here.
Internet.
Yeah.
So I got a question while it's
Yeah.
reconnecting.
Recording stuff. Go ahead, yeah.
So we can only see a super small fraction of the planets out there because the geometry has to work. is that 1% of potentially the ones that, just doing statistically based on an even distribution of orbits and things like that? Is it 1%, 5%?
I think it's about 10%.
About 10% we should be
Yeah,
able
so
to see.
so I mean, we've done estimates and yeah, about 10, we see about 10. I mean, of course, then this is where having astrometry is complementary, right? Then you can get all the face-on systems.
Yeah.
And then hopefully by having all these different methods and then deeper imaging, of course, they want to launch, bigger collecting mirrors like the Habitable World Observatory, and then of course we can try to fill in the parameter space. But yeah, it's sort of about 10% is what we're seeing. So Dave Charbonneau took this. Of course, the first transiting planet was called, ironically, it's in, you recognize Pegasus here, and 51 Pegasus in there, and this phone number 209-458b, which there's probably over 2,000 papers on this star now. This was the first transiting exoplanet. There's Dave Charbonneau, 1999. And can anyone tell me why so this is measuring the brightness over and over again, and then plotting it on that 4-day period. Can anyone tell me why there's no scatter in this light curve? Yeah, there's no errors. We'll see a super-lost light curve later, and there's clouds and vapor, water vapor, so the points go up and down. If you've ever tried to do observing of your favorite object and it's a little bit cloudy or a little bit windy. Anyone want to guess why there's no scatter in that light curve?
Adaptive optics.
Hubble. It's a Hubble data. It's a Hubble data. Yeah, so it's in Pegasus, and then along the same lines, here's this phone number that had a 3-day period, and this just to show you some of these, maybe 1 in 5 of the first 100 exoplanets had these short periods. Like I said, some people were really upset. They didn't believe they were planets. They thought they were star spots. And then there's the terrible joke, why do we know there's no intelligent life on these 3 and 4 day planets? Because who'd want to pay their taxes every 4 days? Yeah. So these.
I don't understand what the scatter.
I'll show you in a minute. In a minute, I'll show you a ground-based light curve, and you'll see that.
You said because it's Hubble.
So Hubble has no atmosphere; it's above the Earth, so it's getting precision photometry, the best that you could buy in
So the
1990.
scatter we're looking at is Earth-based.
Yeah. Let me I'll skip ahead here. You're afraid to look. Where's
Oops.
Did I have to reshare?
I think so. Network bandwidth. Should we just?
So this is a super-WASP. This is super-WASP 1, the first planet detected with super-WASP. You can see that's nighttime observing from La Palma, where you have lots of scatter. So
Earth-based.
ground-based, so that it's not very precise, because you can only sort of measure 1 part in 100 and not 1 part in 10,000. So, Hubble can have excellent precision, and that's why that light curve looks so beautiful. This is what you get from the ground, so it's a bit more difficult.
That's why it stars.
Twinkle, exactly, yes. So in 2003, I was lucky enough to go over to Queen's University of Belfast, and they sort of were working on, and I'll tell you the story more in detail, the List Wide-Angle Search for Planets. And so, does anyone remember 1996? We had 2 beautiful naked-eye comets. We had Hyakutake, and so Don Polacco, who was the PI for the principal investigator for SuperWASP, was asked to build a camera that could cover the tail of Hyakutake and Hale-Bopp, a really large format field of view, and he built something called ComCam, the comet camera. But you'll notice that the stars sort of in the corners here are really blurry. They're kind of elongated, and so it was kind of a nightmare to reduce. So it was too big to sort of look for exoplanets. But then he built a second one, ComCam 2, obviously, and it was only sort of 10 by 10 degrees. And so this is sort of the late 90s after the comets of 1996, and so the light bulb kind of went off as Dave Charbonneau and others were trying to find exoplanets with the transit method. And here's Don, he's with SuperWASP. So Don had this idea, well, if we can use a setup like the comet camera and do with good photometry, that is, you want to measure the brightness of the star as precisely as possible, then we can sort of look for planets, and you're still going to have to go confirm them because you're just measuring their brightness, you know, their sizes as they go in front of their star, but it gives you kind of a shortcut. When you do the radial velocity method, you got to look at each star a few dozen times a night. You can only monitor maybe a few hundred stars a year, and so it's really labor intensive. But now we have this method, and of course Dave Charbonneau sort of proved it with that first star in HD 209458. And so Don had this idea that we could build a SuperWASP. So in 2000, there was sort of a technology demonstrator. People recognize that, good old CA telescope, the workhorse of amateur astronomers, right? And there's sort of a digital camera, a CCD put on the back, and they were able to sort of reproduce. Didn't find any new planets, but it was able to detect the transit of 209458. And so Don got funding from the sort of equivalent of the National Science Foundation in the UK, the STFC, the Science Technology Facilities Council. And so in 2004, we built SuperWASP. And so between 2004 and 2006, I spent 100 nights in that enclosure. And of course, it was slowly becoming robotic. In later years, you just could log in from anywhere in the world and and it would run itself. It would know when twilight is, it would open up, it would take flats. And so
Where was this located?
it's in La Palma, yeah. And so this was SuperWASP 1, and these are Canon telephoto lenses, the 200 millimeter ones. And ironically, of course, Canon goes and changes the format for their digital cameras. So the last few lenses had to be bought on eBay because they didn't exist anymore. And so there I am, and this is sort of the SuperWASP is between the 4 meter and the 2 meter in La Palma. You can see the clouds, we're above the clouds there in La Palma. And it used to be super, super dark there. But since I first went to La Palma, there are 3 more big golf resorts. Can't they play golf in the dark? But anyway, so yeah, so it was a lot of fun to sort of be involved in. When I first went to La Palma, SuperWASP was just a leveled field there, and this is all commercially available stuff. An OMI mount and Canon lenses and Android cameras. Each camera has its own computer, and we don't really want to avoid it. So what's better than one SuperWASP camera? 2. And so Keele University got funding, and there was sort of an argument within the group, St. Andrews and Queens. We wanted to put a SuperWASP on the West Coast, say in San Diego, so that you could monitor the stars for longer every day, right? They would set in Spain, but then you could observe them again on the West Coast. And being an American, that was what I thought would be a great idea, but it never happened. They built SuperWASP 2 here in Sutherland, where the SALT telescope is it has like a 13 meter lens, mirror, but it's only about 11 meters usable. And it's still running. They're still taking data with SuperWASP South. About 6 or 7 years ago, we stopped taking data with SuperWASP North. Don Polacco has moved on to he's a PI for Plato, which is going to be a Kepler-like mission, probably launched in 2026 to put it up in space. And so here's just an example for just 4 cameras. If people remember this nebula, you just saw it in Orion, right? That's M42. So I took some PR pictures, and this, just to show you, this is 15 by 15 degrees, so it's a huge field of view. Each camera has over 10,000 stars. And the William Herschel telescope, the 4 meter, has something called the Wide Field Survey, which is about 0.09 square degrees. MIT Lincoln Labs, they have a telescope in Hawaii. They look for missiles and near-Earth objects with, and that's 4 square degrees. So it was kind of a new type of astronomy where you're looking at a large field of view, and people were a bit nervous because as we got the first bunch of data, we weren't finding any planets, and that is we had to sort of beat the noise down. There's lots of scattered light. There were things that we had to sort of worry about. And so here's sort of the field. Every night SuperWASP would just start out in sort of in the east and step across about 8 different fields and go back and do them all. You know, you get maybe 30-second exposures, you get a few tens of minutes of data on each field with 10,000 or more stars. And so I wrote the first script that sort of did this, and then a young whiz kid named Jonathan Irwin, who was at Harvard for a bit now, and his father was the chair at Cambridge. They used to email each other for dinner. Oh, dinner's ready, here's the Anyway, I digress. So he improved this script, and the telescope kind of became fully robotic in 2006. And then, of course, it's sort of like the old card game where you flip the cards and the stick figures move. You sort of measure the brightness of each star in your field, called photometry, and then hopefully you're sort of measuring this periodic dimming. And so one of the problems is that there's lots of things in nature that can look like a transiting planet. You could have 2 stars going around each other, sort of grazing incidents, eclipses, or you could have a star in the background diluting things. And so, you know, when you have lots of graduate students and postdocs in the first few years of SuperWASP, we would go, everyone got sort of 3,000 light curves to look at, and we found sort of the first handful of SuperWASP planets. But it wasn't easy, and like I said, there was a lot of nervousness because there were predictions that we would find hundreds of planets. Turned out to be a few because it's kind of difficult to do. And as things sort of improved and sort of our friend Timothy Brown, who's up here at Santa Barbara, he wrote a very sort of well-cited paper that you estimate between 1 and 10 planets per 25,000 stars are going to be transiting. Because you have to find them edge on, you have to be lucky enough, there's a windowing function, right? They're only observing at the night. And so it was, people were believing sort of 10 and 25,000 stars. You look at 100,000 stars, you hope for 40 planets, but it was sort of more like 4 planets. And so here's just a sample light curve. I won't talk about the binary star on the left, but this was WASP-1 from sort of 2006. And you can see that little bump there is the planet, sort of a Jupiter mass planet going in front of its host star. But you can see the scatter. It's no Hubble light curve. So how am I doing on time?
You were good.
Good.
Okay.
You did great.
All right. So it turns out then there's sort of 3, nature is tricky. There's 3 sort of things that can make your beautiful light curve look like a transiting planet. There's grazing, eclipsing binaries, which is shown here in this cartoon. If you sort of are unlucky enough to see it at sort of a, kind of an oblique angle, you can have sort of these things that look like transits, but they're actually eclipses. A real big problem with SuperWASP, and these transit surveys have big pixels, so you're looking at a lot of sky at each detection, so you can get dilution from a background star. And then finally, you have to measure it, and it may actually be a brown dwarf. Brown dwarfs are not that much bigger than Jupiter or Jupiter mass planets. And so here's sort of my little cartoon. You have your foreground star that's actually 2 stars. You put a red giant in the, because remember the Milky Way, all those stars we saw in the planetarium, right? There's billions of stars, like 100 billion to 400 million, depending upon who you believe, billion. And so if you turn on that background star, you see it's going to fill in your secondary eclipses, and it's going to make it look like it's actually a planet when it's a star. Yeah, go ahead.
Yeah, so I'm I know you're moving through a lot of technical jargon, but basically we're measuring the light dip.
Yeah, we're measuring the dip as the planet goes in front of the star. Yeah.
and then you're showing what else can create that light
Yeah,
dip.
exactly.
So it's that little dip that is giving us an idea that we're looking
Yeah.
at exoplanet.
Yes. So we go back to the cartoon here. So we're hoping that out of, these 25,000 stars in this image, that we can pick out the few that have a repeating light curve. And of course, as time went on, the software got better to throw out. It could look for
So
secondary.
you're also looking for repeating.
Yeah. Being periodic is very important. The sort of rule was if we didn't see 3 transits, we threw it in the bin. And there's some papers now. There's a paper, I think it's titled One Transit Planets. So it's trying to look at these ones that we only detected 1 transit from, and maybe they're really a planet. We just didn't find. But yeah, so 3 was the minimum. So 3 transits, and try to rule out everything else.
Over how long?
Well, so the hot Jupiters are great because they're transiting every 4 days. So if it happens sort of in the middle of the night, you might see it 4 days later. You might have to wait a month because it's, depending upon how its period and the day-night Earth cycle line up, then yeah. So with the transiting planets, the hot Jupiters, hopefully within a month you can still get a few transits. Yeah.
So you don't know anything else other than you're seeing a light dip.
Yes.
Suggests
Yeah, that's why we have to get rid of these false positives.
an exoplanet.
Yeah.
But now, to do more in-depth study, like atmosphere and that
Yeah.
sort of thing, we haven't got there yet.
No, we have with James Webb. Yeah, I'll show that slide in a minute. Yes, we can, because as that planet's going in front of its host star, we can use the star as kind of a probe. It's the light shining through the planet, and then we can measure what the planet's made of. Yeah, there's going to be a lot of that this year, I'm sure. And so we have the diluted binaries, which is a real pain, because like I said, you have a big field of view. You have lots of stars in each pixel. And then finally, the secondary could actually be a brown dwarf. If you can see here, this is Jupiter, and a brown dwarf, because they're compressed a bit, they're degenerate matter, they're not twice as big as Jupiter, so they can sort of cause a similar transit, a light curve similar to a planet. And of course, we've detected all these planets, now we have to go, candidates, now we have to go confirm them. If you take a sort of a low resolution spectrum, you can sort of throw out a binary star. The rate of velocities you measure are going to be kilometers per second, not meters per second, so you can throw that out. The brown dwarfs you can throw out pretty quickly because they're also going to be more massive. They're going to have tens of meters instead of just a few meters rate of velocities. And then finally, you can do some deep imaging with even a 1 or 2 meter telescope, and you can see if your photometry is being messed up by a background star. And here's an example. This is sort of a super WASP candidate here in this circle. And then I took a deep image with a 2.5 meter where my picture was taken 100 years ago. And you can see it actually has a little companion. And not that that's going to cause an eclipse or anything, but it's going to mess up your photometry. It's going to add light when you don't want any light. So you sort of have to rule out these diluted binaries, which is kind of a big problem. But now, as we've done this now for 20 years, the software has gotten a lot more sophisticated. In sort of the mid-2015, if you had 100 super WASP candidates, more than half would turn out to be planets because the software threw out all the secondary eclipses. You can measure the shape of the transiting planet. It's not like an eclipse. It's not like a V. It's more of a U shape, and so there were sort of more sophisticated techniques. And so planet confirmation, it seems a bit like, oh, you did all this work and now you still have to go to another telescope and confirm that it's a planet. But you have a shortcut because now you didn't have to monitor these stars for very long. You could watch them for a few months and do the photometry. But now you have to go measure the radial velocities on sort of a medium-sized 2 to 3 meter telescope. But that's not that hard. And so here was Super WASP 1 and 2 from 2006. Andrew Collier Cameron was one of the people at St. Andrews, sort of the brainchild behind the data pipeline. But you can see that there's a lot of scatter in there because you measure this
intensity through the atmosphere, right? Like looking through a fish tank. And so WASP 1 and 2, and then sort of a few years later, and then this is the SOFI radial velocity. You just got a few radial velocity points, but they agreed with your transit period, so you were happy. And you can see there's a little artist's conception where this is sort of a K star, an orange star, smaller and less massive than our sun. The planet is sort of transiting near the top. This was sort of a sun-like star where the planet is going across the middle. And so super WASP. And then we sort of divvied up the data, and I published WASP 10, which was kind of a 3-day period, 3 Jupiter mass planet. Nobody cares about, but there was a controversy because it was too big. It was 20% too big for a hot Jupiter, and it probably just is that big. There's been a few papers on that. But. So here's sort of WASP 1 to 15, and now WASP is published about, there's about 190 planets now with over 100 published, and there's probably a few more in the data pipeline. Like I said, Keel, Super WASP South is still taking data. So before I go to the last part, are there any questions? Did I lose you at the bakery? Yeah, go ahead.
Any of the stars that are pretty well known, have they found exos around Vega and Sirius and
Well,
Betelgeuse?
one of the more exciting ones was Proxima Centauri has a small planet.
Well, that's their
Yeah,
next door neighbor.
yeah. I think Vega has a planet, but I don't quote me on that. I'll have to look. But yeah, so like there've been for years they've studied Barnard star, thinking I think the jury's still out on that one,
But if you don't get the solar system edge on, the only thing you got is the wobble.
yeah. Then you have to go do astrometry or some deep imaging.
But
And
a
those,
planet the size of Earth wouldn't make it much of a wobble, would it?
no, it's centimeters per second, and so the radial velocity people are building more accurate spectrographs to try to do that from the ground. But the best way to find Earth-sized planets right now is transit photometry from space. So I'll talk about it in a minute. You had a question? Yeah. No.
Do most stars have planets?
Yeah, I think that it's pretty established that they form. There's a protostellar disk that clumps, and you get some differentiation. And so, yeah, I would think there was a time when the number was only a few % of stars have planets, but now I would think it's pretty much every star has a planet. Go ahead, yeah.
So what's most amazing to me is that you collected this data with what is, good amateur equipment.
Yeah.
It was a 200 millimeter Canon lens, maybe what, 4-inch, aperture, 4 or 5 inch?
Yeah, it's a.
Yeah, and a CCD that, what resolution? Like 2000 by 2000?
No, they're 1K by 1K.
1K.
Yeah, so the pixels are at 14 arc seconds. Yeah, they're and/or cameras. They're about 25K each, and the price keeps coming down.
Yeah, but no,
Yeah.
that sort of equipment is available to amateurs right now.
And
And so-
amateur astronomers have better equipment.
Yeah, exactly. I just can't believe, I've heard of WASP, but I didn't
Yeah.
realize that it was done with equipment that is at that
Right.
scale. It's great.
Yeah, and now there's in sort of Doug Blockman, the group have built something called the Next Generation Transit Survey, the NGTS, and that's 12 cameras, and it has much more sensitive digital cameras.
Sure.
And it's found some Saturn size, things. Goal sort of from the ground is to try to see things that are about 4 times the size of the Earth, so your Neptunes and your ice giants. So that's happening now, but because Kepler was launched, now we have NASA's TESS, which is also like Super WASP in space.
Yeah.
There hasn't been a big push to do ground-based photometry of exoplanets, because everyone figures TESS will do it better from space. But there's still a lot to do there, and there's a handful of amateurs. All this data is public, right? You can go to the Space Telescope Archive or download Kepler data and look, search it to your heart's content and find planets still. Not that you want to spend your weekends like that.
Club needs to mark planet.
Yes. The SB, yeah, go ahead.
In 2014, this club sponsored a nuclear hydro, and so
Okay.
we built a barn door tracker, and she used a camera lens and a camera, and she was able to generate the curve, Schlitt's curve,
Oh, nice.
for a known exoplanet.
Oh, great.
And we discovered
Yeah.
saw it.
so one of the big advances in that, you know, 3/4 of all the exoplanets known now came from NASA's Kepler mission, which was launched back in 2009. So here's sort of the image we had from superWASP, where a Jupiter-sized planet going in front of its sun-like star, so it's dimming the light 1 part in 100. But the Earth, of course, is 10 times smaller than Jupiter, so there's the Earth. So it's 1 part in 100 in terms of radius, and then it's 1 part in 10,000 in terms of the brightness. In order to measure that small change, you need to go into space. And so Bill Barucki had this idea from years and years ago, and they had a little prototype called Vulcan at Lick that ran for years. It didn't find any exoplanets, but it was sort of a test bed. And so, you know, this is, people were really skeptical that we were going to find a lot of Earth-like planets, and I think Kepler's probably found about 400 Earth-sized planets. And now, of course, its reaction wheels went, so Kepler's not working anymore, but Tesla's working now. So one of the big goals then is to try to find liquid water around one of these Earth-sized planets, something called the habitable zone or the continual habitable zone. And so this diagram here, there's an artist's conception of an Earth-like planet, but this blue line, as you go from the upper left on the ordinate here, you have a bright hot star hotter than our sun. Then you go down to something cooler than our sun that's a red dwarf, and you can see that you can move closer to the star and still not have your planet be fried because it's much dimmer than our sun. And so this blue line is where you can have liquid water on the surface of your planet. You can see Earth is nicely in the continuous habitable zone of our sun. There's Mars, and of course Mars is a problem, right? Because it's only 1/10 the mass of the Earth, so it's really hard to hold on to an atmosphere. You got to send Matt Damon, he's got to bring all that equipment, build a biodome. And Stephen Kane at UC Riverside, he gives a great talk about Venus. Venus is sort of the Earth's twin, although it has this thick CO2 atmosphere and it's 900 degrees. If you could terraform Venus and get rid of all that sulfur dioxide and nasty stuff and the pressure and the temperature, it's probably a better place than Mars. But what do I know? So it's sort of sometimes this was a planet from over 10 years ago that is around a small red star that could have liquid water. Had that phone number, Lisa 581, I think. And then sometimes they talk about the Goldilocks zone. You know, Mercury is too hot, or Venus is too hot, Mars is too cold, and the Earth is just right. And so people are looking, we want to find these Earth-sized planets. It doesn't really have to be Earth-sized, but we want it in the continuous habitable zone. And so the press gets really excited about exoplanets. There's the one I mentioned, and then this is a recent article on space.com, and it's sort of interesting, some of the Kepler planets that were discovered over 10 years ago are still kind of the record holders. And just to mention, so Kepler was kind of a simple spacecraft to save money. It only looked at 1 part in Cygnus. You don't want to look in the galactic plane because that would be like looking at a Christmas tree through a fish tank, right? There are just too many stars, so you want to stay out of the galactic plane. But it's 30-some detectors just stared at about 150,000 stars in Cygnus, and it had to rotate every 90 degrees for the solar panels, and it sort of was wildly successful. So Kepler 11 had 6 planets, you know, lots of sort of transiting light curves that have planets, and then one of the more famous ones is this small, it's a system with 7 planets called TRAPPIST-1, and you know it's really famous because you can buy the t-shirt. but it's sort of like a mini solar system, and people have even mentioned that, and I won't read all the details, you can look at it, it's sort of like a mini Jupiter in the sense that it's got sort of similar scales to the Galilean satellites and things. But this one here is sort of one of the more famous Kepler 22b, the 22nd Kepler exoplanet. It's about 2.5 times the size of the Earth, but it has kind of a nice 300-day orbit. So that's still, I think, one of the record holders for a possible habitable planet. And then this one was sort of the smallest over 10 years ago, and I think it still is. It has this 1/3 of Earth size. But see, this is one of the bad things about the Kepler planets, is they're too far to get a radial velocity from Keck or a big telescope, so people kind of guess. They think, well, this has an Earth-like density, then we know the mass, but we don't really know what they're made of, so there's a little bit of speculation going on, but never really. And then finally, sort of the last little piece is the fact that, and there's only 2 slides on this, the fact that, as the exoplanet goes in front of its host star, the transit for Jupiter-sized planet in the short orbit is about 2 to 3 hours. So you can add up the spectra of the light going through that atmosphere. You can see hopefully water or methane, and if it has life, maybe you would see ozone or some biomarkers. And so then this was one of the big goals for the James Webb exoplanet sort of studies. And James Webb is an amazing instrument, but there are stars that can't look at because they're too bright. You would damage James Webb if you looked at some of the brighter stars. And so this was kind of an old result with Hubble, where from our favorite 209458, they sort of thought they detected water in some of these images, photometry taken by Biddle Major in 2003. And this paper is a little bit controversial, but it sort of just shows you the concept that by looking at the light pass through the atmosphere, and of course an Earth-sized planet, even in a short orbit, it takes more like 16 hours, so you get a lot of data to try to measure what's in the atmosphere. And this is what an Earth-like planet would look like simulated for James Webb. The thing everyone was talking about is ozone here at about 9.6 microns. And of course, this is in the infrared channels. And Dr. Lowe worked on this. This is a pretty amazing spectrometer. And there was just a press release where they are claiming to have seen DMS, dimethyl sulfide, that would be a biomarker around Kepler. And so K2, when the reaction wheels started going at Kepler, it couldn't sort of do the precision for the Earth-sized planets, but it still detected planets that were more massive, and they called it the Kepler 2 mission, and that ran a few years. So K218, that's sort of from the second act, the sequel of Kepler, and so they have a nice transit spectrum of that Kepler 18, and people are, if you look, the blue line is actually the model. The data's not quite as good, but there's going to be, I think this year, definitely some detections that we see for different things we haven't detected before on nearby planets orbiting their stars. So that was pretty much it. The quick summary then is we have over 5,800 planets tests. There's about 7,000 candidates. Only about 600 are confirmed, but in the next few months, this number is just going to keep going up and up. SuperWASP contributed about 190 exoplanets, and you might think, well, what's the point of finding more and more hot Jupiters? Well, it's nice to sort of get a lot of these SuperWASP objects have become candidates for James Webb and follow-up. But also, as you improve your sort of detectors, you can see smaller and smaller planets from the ground. And of course, TESS was launched a few years ago. It's sort of like SuperWASP in space. Unlike Kepler, it can look all over the sky. So like I said, it has about 600 planets confirmed, with several thousand to be confirmed. Don Placco's involved with a space mission-like test called Plato, which is scheduled for a 2026 launch. And the Roman Space Telescope is supposed to be launched in 2027, and that's going to be sort of like a Hubble, a 2.5-meter space telescope. And it's going to be looking for distant supernova and also exoplanets. Originally, it was called the Wide Field Survey Telescope, and so it's hard to keep track, we keep changing the name. And then there's a small telescope called Cheops, but then Hubble is still going, James Webb, and of course, you know, we want to see if there's any life in the galaxy and possibly intelligent life. But thank you. I'll take any questions. So there's the sunset over Super Wasp. If you look closely, there are only 5 cameras there, so it was 2004. Great. Well, thank you.
Dr. Damian J. Christian, California State University, Northridge. Another big round of applause. I got something for you, Doctor, but I wanted to say that I got him through a friend of mine who's going through post-surgical things. I think he's a doctor too, Gerald Jackman. Yes. Gerald Jackman used to run the Presidio. And he's a friend of yours. And he wanted to be here with his wife Michelle, but probably has problems post-operatic surgery. But his good friend smokes cigars with him in his backyard all the time. Is this front row gentleman who did one of our in-house members-only speeches 2 Decembers ago. Thanks for coming, folks.
Thank you.
We're always here first Friday. And this is Mike Hardwick, and this is our man, and the rest of you, listen, I'm going to take care of you right now. I got one of our priceless porcelain cups, which were designed by the Chumash, and they've been unearthing back here. Also have an honorary check in there.
Thank you very much.
Thank you.
Thank you very much. It was fun.
Jerry Wilson, you want to end the meeting officially? And thank you, Tessa. Who are we forgetting? Is anybody here that we should? Tom Whittemore's here, edits our newsletter, I think, isn't he?
Yeah.
Everybody's here. Could we turn the heat down a little bit? I like this place.
It's better, I'm sorry, this is indoors.
Oh, it is intimate. I like to leave my bed alone.
Anyway, this meeting's officially closed.
I sent you an email today.
What's that?
Probably haven't seen it. I sent you an email today.
Oh, yeah?
So, Santa Claus brought me a Richie Chrétien for Christmas.
8-inch?
Yeah, 8-inch Apertura. And I ordered something that could be covered from the back mirror so you get really good collimation. And I found this guy in the Netherlands who had a really cool procedure. So created a really good artificial star. And you basically take Newtonian, so like a 8 or 10 inch Newtonian, right? And you have a laser source at the focus of that. You get a collimated beam coming out, a 10-inch collimated beam, that you can then sit right in front of your scope, and it lets you do star testing. I mean, no whatever like that. Just and brilliant idea, because we all know about collimating lenses, right? So you just use a big scope, it's well collimated, to create a collimated beam that can go into the scope that you're working on, and it's beautiful. I just don't have it. And so I was wondering, do we have
Being an 8-inch, you have FCT.
do an 8-inch SCT? Okay, that would work. The same thing. Is there one that I could borrow for a month or something like that to try to play with this and see if I can?
So you're beaming the laser through the backwards through the scope.
Yeah.
And so your execution is looking, where's it looking at now?
You put them looking at each other. And I in the email I actually pointed you to the links. And it's like the more you read about it, you go, this is
So, you really should tune in with the guys on Tuesday evening, and talk about this. Next Tuesday at 7:30 Zoom.
yeah.
We have our link to Yeah, folks should be interested in that.
Well, let me try it first.
Yeah, no, but I mean, discuss it. I mean,
Yeah.
What do people say about it?
Are those
Sharp guys. Jerry Wilson.
those meetings are recorded?
No,
They're not
they're
recorded.
not recorded.
Okay.
Jerry didn't want to include.
I
People can say things and they don't want to be recorded.
yeah, because the other thing is recorded, right?
We're recording this right now.
No, I'm talking about the thing, the other Astro Hour thing. That's